All right, today we're diving into a world of incredible power, but also microscopic weaknesses. We're going to go deep, really deep into the science of the brake. We're talking about why some of our most critical, most powerful machines suddenly fail, and what engineers are doing to stop it. This is going to be fascinating.
So let me ask you something. What in the world connects a massive, modern wind turbine to the landing gear of an aircraft? Think about it. One is harnessing the wind, the other is taking this incredible violent force of a landing. They seem like they're from totally different universes, right? But they share this one critical common vulnerability. Any guesses?
Well, if you guessed the gear, you'd be right. It all comes down to one of engineering's oldest and, frankly, most essential inventions. These little toothed wheels, they are the invisible workhorses that translate power into motion in pretty much everything, from those giant turbines to that landing gear. They are absolute marvels of precision engineering, but, and this is the big but, when they fail, the consequences can be, well, catastrophic.
Okay, so here's our game plan for this explainer. First, we'll talk about how the world literally runs on gears. Then, we'll get into the nitty-gritty, the anatomy of a failure. After that, we'll look at how we can listen for cracks before they happen. Then, forging a stronger gear. And we'll wrap up with something really cool, a future that is programmable.
First up, the world runs on gears. And, it's really not an exaggeration to say that. They are the hidden heart of countless machines, just humming along silently in the background. But here's the thing. This total reliance means that one single point of failure, one tiny gear breaking, can create a massive, massive ripple effect.
And get this is the key point. Gear failure is not some rare freak event. Not at all. The research is pretty clear. Over 30% of all failures in any kind of rotating machinery, we're talking industrial pumps, power generators, you name it, can be traced right back to the gearbox. It's kind of like the Achilles heel of modern mechanics.
Okay, so that brings us to the big question. Why? Why do these incredibly precise components, forged from some of the strongest metals we have, actually break? Well, failure is almost never a single dramatic snap. It's more like a story that's written over time by stress, by the environment, and by tiny microscopic imperfections.
And one of the very first signs of trouble is something called pitting. Just look at this. Research from Wren and his colleagues shows how these tiny little crater-like cavities start to form on the tooth surface just from repeated stress. They look small, right? But you should think of each one as a tiny red flag, a warning sign that a much bigger, much more serious failure could be on its way.
But pitting is really just the symptom. The root causes? Oh, they are all over the place. As studies from researchers like Deng, Gerges, and Subban show, failure can come from almost anywhere. The metal itself can just get tired, Material fatigue. Corrosion can literally eat away at its strength. The lubrication can fail, which causes the surfaces to scrape and fuse together. That's called scuffing. Or maybe the gear was just flawed from the very beginning because of a tiny, tiny error in manufacturing.
All right, so knowing why gears fail is one half of the battle. But how do you actually catch a failure before it happens? This is where things get really interesting. We're stepping into the world of predictive maintenance, where scientists are literally learning to listen to machines for those telltale signs of distress.
And there are two main ways they do this. On one side, you've got vibration analysis. Think of it like a super advanced stethoscope. Researchers like Medeiros and Mansi use these incredibly sensitive tools to just listen to a gearbox's vibrations. Tiny, subtle changes in that vibration pattern, when run through some complex algorithms, can reveal the very earliest stages of wear. Then, on the other side, you have thermal analysis. This method, which folks like Tourette are exploring, doesn't listen, it watches, it looks for heat. A fault, like a tiny crack, is going to generate extra friction, and that creates a hot spot, basically pointing a thermal finger right at the problem.
And this thermal method is incredibly systematic. Check out this 6-step process from Tourette's research. It's pretty brilliant. First, they build a perfect digital model of the gearbox, so they know exactly what normal heat looks like. Then they simulate what different kinds of faults would look like thermally. A crack here, a worn tooth there. This creates a whole database of fault signatures. Finally, they measure the real operating gearbox's heat signature and just compare it to their database to find the match. It's literally like matching a thermal fingerprint to a list of suspects. Predicting failure is absolutely crucial. But what about stopping it from ever happening in the first place? That brings us to the proactive side of things, building fundamentally better, stronger, more resilient gears, right from the molecular level.
And it really all starts with the material itself. This table shows data from a study by HireMath,
who took 3 different types of steel used in gears and applied a special heat treatment called normalizing. Now just look at these results. It's incredible. The tensile strength of the EN353 steel, that's how much you can stretch it before it breaks, it just skyrockets. The hardness of the 20MnCTR5, its resistance to wear and tear, hits its absolute maximum. And the toughness of the EN3, its ability to take a punch becomes superior. This one single process dramatically upgrades the core properties that prevent failure.
But here's the thing, you can have the best material in the entire world, and it will still fail if the design isn't perfect. The actual geometry of the gear tooth, that is an entire field of science all on its own, dedicated to managing these immense forces. So engineers use these unbelievably sophisticated techniques. As Han and Shi describe, they make microscopic tweaks to the shape of the tooth. It's called modification, to better spread out the stress. You've got researchers like Zhu creating these complex computer models just to predict exactly how the lubricating oil will behave under intense pressure, all to prevent that scuffing failure we mentioned. And check this out. Chan's work shows they're even using AI to run millions of simulations to predict the fatigue life of gears in something as critical as an airplane engine. Wow. So, we've seen how we can predict failure and how we can prevent it. But this last part of our journey, this is where we look to a future that honestly sounds like it's straight out of science fiction. We're talking about a world where the gear itself is no longer just a static, fixed object.
Take a look at this quote. It's from a really groundbreaking paper by Xin Fang and his team. They write about, quote, a metamaterial design paradigm that enables continuously tunable elastic properties, allowing shape morphing between ultra-soft and solid states. Now the key phrase there, the one that changes everything, is continuously tunable elastic properties. This is a complete paradigm shift. So, what does that actually mean? Well, imagine a gear that isn't just hard. Imagine a gear that can actively decide how hard it needs to be at any given moment. It could go soft to absorb a sudden violent shock, and then, in an instant, become rigid again to transmit power efficiently. We are talking about a gear that can adapt to its environment in real time.
And this chart really shows you the massive leap we're talking about. A traditional gear, it has one stiffness. That's it. It's fixed. The metamaterial gear they're talking about in this research, it can adjust its stiffness over a range of 2 orders of magnitude. That is 100-fold difference. The level of control this offers is something mechanical engineers could have only dreamed about until now. It's a game changer.
So, there you have it. From the forensic analysis of a tiny crack to designing materials that can practically think for themselves, the science of gears is constantly pushing forward. And it really leaves us with a fascinating question, doesn't it? The whole story of engineering is this relentless cycle. You identify a weakness and you innovate a solution. So as we get closer and closer to engineering the perfect, unbreakable, adaptable gear, what's the next unseen weakness that's going to be waiting for us just around the corner?